This lecture explains the basic concepts of the heat transfer through the building envelope. In particular, the energy moves from a hotter to a colder object by three mechanisms. Conduction, when two objects are in physical contact. Convection, when heat is carried by a moving fluid, for example water or air. Radiation, when electromagnetic waves carry heat from one object to another. Let's start with conduction. When a solid body is heated, the heat is transmitted due to conduction from one end to the other. The atoms of the warmer part of the body transmit their greater thermal agitation to those next to them, and the body progressively increases its temperature. When the body is heated continuously from one part and has reached the steady state, the temperature gradient through it is linear. This is the case of an homogeneous wall heated on one side. The thermal flux Qc, which is the amount of the heat transferred per unit of time by conduction through an homogeneous wall of area S capital and of thickness S, is calculated by this formula, where Qc is the thermal flux expressed in Watt. Ts1 and Ts2 are the temperatures of the phases 1 and 2 in Kelvin. S is the thickness of the plate or wall in meters. Lambda is the thermal conductivity of the material in Watt on meter Kelvin. S on lambda is the thermal resistance of the material constituting the wall in square meter Kelvin on Watt. Capital S is the area of the wall in square meters. The flux is directly dependent from the temperature difference and inversely dependent from the thermal resistance, and thus from the conductivity. The thermal conductivity is a specific property of each material, and it defines the higher or lesser ability to transmit the vibration of an atom to the continuous ones, which means to conduct the heat from one point to the other. It is dependent on the temperature, the density, and the moisture content of the material. Typically, low-density materials, such as polystyrene, have also low thermal conductivity, while those with high density, such as concrete, have elevated thermal conductivity. Actually, the heat flow across a wall is not constant, because the outside air temperature changes in a cyclical pattern throughout the course of the day. So, the heat capacity also comes into play, and the heat flow through a wall varies over time in different ways, depending on the resistance and the specific heat capacity of the material. It can be noted that the actual heat flow curve is delayed in comparison with the outdoor air temperature curve by some times. This delay of the peak is defined time lag and is measured in hours. The actual peak heat flow, when mass is taken into account, is also reduced by the effect of the mass, and this effect is added to that due to thermal resistance. The ratio of the real peak heat flow to that of the ideal wall with zero thermal mass is defined decrement factor. The external conditions strongly and quickly influence the internal temperature in lightweight buildings with low mass. Massive buildings with high time lag have better performances, especially during the hot season. Placing a lightweight insulating material on the outside of a massive wall will give a time lag and a decrement factor greater than that of a massive wall alone. In the second mechanism, the convection, when a fluid flows around a warm and solid body, the thermal agitation of the solid body is transmitted to the molecules of the fluid, which increase their speed, and the fluid is heated. In this case, since the portion of the warmer fluid that is in contact with the solid has a lower density than that of the rest of the fluid, it tends to move upwards. On the contrary, if the fluid is warmer than the solid body, the part in contact loses heat and it cools down. Its density decreases and it tends to move downwards. The thermal flux Qconv due to convection is calculated by this formula, where Hc is the convection heat transfer coefficient in Watt on square meter Kelvin. Capital S is the area of the wall in square meters. Ts and Tf are respectively the surface temperatures of the solid body and that of the fluid, in Kelvin. Regarding the third heat transfer mechanism, it must be noted that electromagnetic radiation can also be seen as a group of photons, whose associated energy is a function of the wavelength traveling in the space. When a photon hits an atom, an increase in thermal agitation is generated. When the temperature of a body is increased, the amount of radiant energy, QR, that it emits can be calculated according to the Boltzmann law, where QR is the radiant heat flux in watt, epsilon is the emissivity of the surface, which is the ratio of the radiant flux emitted from the real body and that emitted from the black body at the same temperature. Sigma is the Stefan-Boltzmann constant in watt on square meter Kelvin to the power of 4. S is the area of the emitting surface in square meters. T is the absolute temperature of the emitting surface in Kelvin. An object not only emits but also receives radiant heat, being surrounded by other bodies. What matters is the net balance of energy, which is the difference between the radiant heat emitted and the radiant heat received. This balance depends also on their positions, which determine the reciprocal apparent surfaces. The greater is the apparent surface, the greater is the amount of radiant energy the body receives. To quantify the phenomenon, the view factor, FPI, called also form or shape factor, is used, indicating the proportion of the radiant which leaves a person P that strikes a surface I. There are 4 ways in which the electromagnetic radiation interacts with matter: transmission, reflection, absorption, and emission. Transmission takes place when radiation passes through a material. Reflection when it is reflected by the surface. Absorption when radiation is absorbed and converted into sensible heat. Emission when the material emits radiation from its surface. It always has this relationship, where tau, rho, and alpha are respectively the transmission, the reflection, and the absorption coefficients, dimensionless. For most of the material commonly used in construction, emission is equal to absorption. When the surfaces of a building are hit by solar radiation, the external surface temperature increases depending upon the incident solar radiation and the absorptance of the surface. This phenomenon can be taken into account by virtually increasing the external air temperature to an appropriate value to obtain the same effect. This increased value is called Sol air temperature. The flow transmitted through a building surface due to Sol air temperature, QSA, can be calculated with this formula, where Q is the heat flow due to actual external air temperature in watt. Alpha is the absorption coefficient of the surface, dimensionless. IS is the total solar radiation incident on the surface in watt. In conclusion, by calculating the conduction, convection, and radiation heat fluxes, it is possible to evaluate the total thermal flux through a building surface.